So, let us do some more problems on central forces, especially inverse square attractive central force. And the first question is this: an object of mass m is projected from the earth's surface at an angle of 60 degrees from the vertical with a speed v naught equal to square root g m by r, where m is the mass of the earth and r is its radius. So, you have earth, and then you are somewhere here, this is vertical, and from the vertical making an angle of 60 degrees, the particle is projected with some speed v naught, which is given here. And then the question is, find the maximum height the object attains. So, you must have done such problems in class 11 or even maybe even before, but then the speeds were in meters per second, and here the speed is much larger. It is in terms of mass of the earth and the radius of the earth, and the speed is square root of g m by r, which will be in kilometers per second. So, that is why the approximation of constant g cannot be taken here. So, we know this particle will be attracted by the earth, and the force of attraction will be minus g m m over r square, which is of the type minus k by r square we have studied, with k is equal to g m m. So, it is inverse square attractive force under which it is travelling. So, it will go in an elliptical path and hit somewhere. So, we want to know, maybe it will hit somewhere or may not. This is the maximum distance, this is the maximum height. You know, height is the distance from the center. So, I should draw a slightly better diagram. Okay, it won't be better because this is not circle. Fine. So, we need this r max from the center of the earth, the farthest distance, that is the height, maximum height that is obtained. In fact, this is the maximum height minus this capital R, but nevertheless we will call this as r max in our terminology. So, it is going in ellipse and I want to know what is r max. Okay. So, what should be our strategy? We have to get this maximum value of r, and you know, this maximum value of r for inverse square attractive force is given by L square by m k and divided by 1 minus eccentricity. This is r max, and r min is this quantity divided by 1 plus e. And what is this e? Eccentricity. This is the square root of 1 plus 2 u L square divided by m k square. So, our plan will be to calculate L and u. L is a constant of motion, u is a constant of motion, and we can get the values of L and u from this initial point. We can calculate L here, we can calculate u here, and those values will remain same as it goes in this elliptical orbit. Okay. So, we calculate u and L. Once we calculate u and L, then we can calculate this E, and once we have this E here and L we calculate, then we can calculate this r max. So, that is the strategy. So, let us calculate L and then u. So, what is L? At this point what is L? M into V into R into cos sine whatever sine 60 degrees, right? Because only this component, this tangential component will contribute in L, r cross p. This radial component r cross p, this will give 0, and this component is v naught sine 60 degrees. So, mass into this v naught sine 60 degrees into distance capital R, that is our L. So, this is m, and v naught is given to us g capital M by R. and then this r here, and then this sine 60 degree root 3 by 2. So, let us take everything inside. Let us take everything inside this square bracket. So, this is r here, this is r here. So, let us take everything inside. This m becomes m square, capital G is there, m is there. This r will come inside as r square, and with this r it will be capital R here, then 3 by 4. So, 3 by 4, that is L, and this L is calculated at this point, but this is the L everywhere in the whole of the orbit, whether it hits here or whether it goes in another path or whatever it does. Okay, then U is kinetic energy half V naught square, and potential energy, we are talking of this point, minus G m over r. At this point the distance is r. So, it is this, and this is half m. V naught square is G m over r, that is V naught square, and then minus G m divided by r. If you take this G m by r common, it is half minus 1. So, it is minus G m over 2 r, that is it. Now, let us calculate this eccentricity E, and for that you have this equation. So, first let us calculate this quantity, 2 u L square divided by m k square is equal to 2 into u is minus G m over 2 r into L square. L square is 3 small m square, then G m capital R and divided by 4, that is L square. So, 2 u L square divided by m k square, m, and k is G m square of that. So, G m and then small m and square of that. So, G m square and m square, it is like this, k square, G m square and m square. So, m square, G m square, that is our k square, and this m here. And now, see what simplification can be done. So, you have G m here, you have G m here, and you have G m square here. So, they cancel out, right. Then you have m here, you have m square here, that is m cube, and you have m here and m square here, they cancel out, m cube cancel out. You have this r here, you have this r here, you have this r here, that cancels out. So, what is left? Only the numbers, only the numbers. And what are those numbers? This 2 can be cancelled with this 2. So, it is minus here, and then this 2 is already gone, this r is gone, G m is gone, into 3 by 4. So, into 3 by 4 is here, and that is all, and that is all, everything else has cancelled out. So, this quantity is minus 3 by 4, and therefore, eccentricity is equal to square root of 1 plus this whole quantity, and this whole quantity is minus 3 by 4. So, this is 1 minus 3 by 4, and that is square root of 1 by 4, and that is half. So, the eccentricity of this ellipse, the object is going on an elliptical path, and eccentricity of that is 1 by 2. So, what is R max? R max is here, L square by m k divided by 1 minus E. So, R max is equal to L square is here, L square. So, 3 m square g capital M r divided by 4, that is L square, divided by m k, small m and k is g m m, right, g m m, k is g m m. So, we have written L square, that is L square, then divided by m and then this k, and so this is L square by m k divided by, the whole thing divided by 1 minus eccentricity, that means 1 minus half. So, once again you have m square, m here and m square here cancel out, g into m cancel out, and what is left, 3 into r here, and then 4 here, and then half here, that will go up. So, that will become into 2, and this is 3 r by 2. This is r max. From the center to the highest point is 3 r by 2, and therefore, the height, maximum height is 3 r by 2 and minus r, and that is r by 2. So, that is the maximum height over the ground. So, our next question is this. You have this diagram and read the question in its reference. A spacecraft is going in a circular orbit of radius 2r around the earth. So, here is the earth and this spacecraft is going in a circular orbit of radius 2 times r, where r is the radius of the earth. It is to be taken in a circular orbit of radius 4r. So, it is going in this orbit, but then it is to be taken in this circular orbit whose radius is 4r. The first part is, what is the minimum energy to be spent in this operation? So, minimum energy to be spent is same as the increase in energy as it goes from this circular orbit to that circular orbit. That much we have to do if there is no other waste. Okay, so, part A, energy in orbit of radius 2r. So, when it is in this circular orbit, what is the energy? So, you can write the energy. You have total energy is equal to kinetic energy plus potential energy, and the kinetic energy you can easily write, if m is the mass of the spacecraft, mv square divided by the radius 2r, this should be the force, and that is g m m divided by 2r square. Okay, so, this is the force on this spacecraft towards the center, and that force should be equal to mass times acceleration. So, here is the mass and here is the acceleration, v square divided by the radius of the orbit. And so, half m v square is equal to this, r goes on that side, so g m m by 4 r. So, that is the kinetic energy, and the potential energy here is minus g m m and divided by 2 r. So, what is the total energy? The total energy is g m m divided by 4 r and minus g m m divided by 2 r, which will be minus g m m divided by 4 r. Has to be negative. For the bound orbit, the total energy must be negative in at least in this inverse square central force, attractive force. Then energy when this goes to this orbit, this circular orbit, in the second orbit. So, that energy in the orbit of radius 4r is in a similar fashion. You can write V m times v square divided by 4r is equal to g m m divided by 4r square, and that gives me mv square. Half mv square is equal to 2r will go on that side. So, g m m, and here it should have been 16r square, but 2r is here. So, 8 times r, right, 8 times r, that is the kinetic energy. And then potential energy, you can write potential energy is minus g m m divided by 4r when it is at the distance 4r. So, the total energy is, in this case, is total energy is g m m over 8r and minus g m m over 4r, which is equal to minus g m m over 8r. Very simple. In fact, in place of 2r you have to write 4r. So, in place of r you have to write 2r. So, it has to be minus g m m by 8r, which is here. So, how much is the change in energy between this smaller circular orbit and the larger circular orbit? So, the change in energy is equal to this energy minus g m m over 8r and minus the energy in the previous orbit, which is minus g m m by 4r. And how much is this? This is g m m by 4r minus g m m by 8r. So, it is plus g m m by 8r. Right, this is positive, this is negative. If this goes to that side, it will add, and then it will be double of this, and that is this. So, this much is the increase in energy. That much energy has to be supplied to the spacecraft, and if there are some other form of energy wasted, then that will be more, but minimum this energy is to be spent if you want to take this spacecraft from this orbit to this orbit. So, that is part A. So, part B, it is to be done in 2 stages. In the first stage, rockets are fired at point A, taking it to an elliptical orbit with the nearest point at a distance 2r and the farthest point at a distance 4r, as shown in the figure. So, in the first circular orbit, when it is here, rockets are fired. So, what are the rockets going to do? Change the speed, and because of this change in speed, the energy is increased and it goes in an elliptical orbit. Remember that V effective R graph, it has a minimum. If the radius or the energy is at the bottom of that, it is circular orbit, and if you increase the energy, then you have 2 turning points R1 and R2. So, you have R minimum and R maximum. So, that elliptical orbit is here. It is the minimum distance is this much 2r, and this elliptical orbit, the maximum distance is 4r, and it reaches B. So, that is the first stage, to take it from the circular orbit to this elliptical orbit. So, this is it, and find the change in the speed at A when the rockets are fired. So, this is it. Now, so we are going from the circular orbit of radius 2r to this particular elliptical orbit, and we are asked how much is the change in the speed. So, energy when in the circular orbit of radius 2r is say E1, we have just calculated it, that was minus gmm over 4r. We calculated kinetic energy, we calculated potential energy, we added to get this energy. There was a simple procedure, and that is, if you remember, the energy is minus k by 2a for any elliptical orbit under inverse square attractive force. The energy is minus k divided by 2a, and this 2a is the major axis, a is the semi major axis. So, if you have a circular orbit, then this major axis, minor axis are same, and that is here to here, and that is 2 times the radius, and this is radius is 2r. So, 2 times the radius is 4r, and k is of course gmm. So, it is minus gmm and divided by this is the radius. So, it is 4r. So, there is a simpler way of doing it, and I will be using it for the elliptical orbit. Okay. Now, for the elliptical orbit, energy when it goes to the elliptical orbit, E2, let us say that E2 will be equal to minus k by 2a. So, minus gmm by 2a. What is 2a? This minimum distance here is 2r, and the maximum distance here is 4r, and the major axis is 2r plus 4r, that is 6r. So, it is 6r. So, this is the energy, it is here. From here you can get the velocity, because half mv square and minus gmm by 2r, that is the energy, kinetic energy and plus potential energy is equal to minus gmm over 4r, and therefore half mv square is equal to, this will go to that side and it will be gmm over 4r. So, m cancels out, and therefore v square is equal to 2 goes here, gm by 2r, and so v is equal to square root of gm over 2r. And what happens here? Total energy is given. The total energy is half mv square, that is the kinetic energy, and minus gmm. Remember, I am here, we are talking here, we are going in a circular orbit, and now we are changing to elliptical orbit, and what is the change in the speed that is asked. So, the potential energy remains the same, minus gmm by 2r, and this is the total energy. So, this is equal to this and this. So, what is half mv square? Half mv square is equal to, this comes this side, gmm over 2r, and then minus gmm over 6r. So, 6r here, and this is 3 times, and this is minus 1 times gmm. So, this is gmm over 3r, and therefore, v square is equal to, m will cancel out from here and here, and this 2 will go there. So, 2 times g capital M by 3r, and so v is equal to square root of 2 gm over 3r. So, when the rockets are fired and it goes in the elliptical orbit, the energy is increased, and the new energy is given by this quantity, and that is sum of kinetic energy and potential energy, and from there you can calculate that the new speed should be this, old speed was here, and therefore the change in speed is equal to this energy, final energy, square root of 2 g m over 3 r, and then minus square root of g m over 2 r. That is it. So, if you take this square root of g m by r common, what you are left with? Square root of g m by r common. So, this is a square root of 2 by 3, this is square root of 2 by 3, and then minus square root of 1 by 2. So, square root of 1 by 2. And check that this is positive. It must be positive. We have given energy, we have increased the speed. The total energy is more in elliptical orbit. So, this is 2 by 3, that is 0.67 or so. This is 1 by 2, 0.5. So, this is positive. So, this much of increase in speed is occurring at this point A. All right. So, that is part B. Part C. In the second stage, rockets are fired when the spacecraft is at B. Here, the rockets are fired here in its elliptical path. This takes the spacecraft to the final circular orbit, that means to this final circular orbit of radius 4r, and again you have to find the change in the speed in this operation. So, exactly similar procedure. You know how much is the total energy when it was in elliptical orbit before firing the rockets, and that is here, energy when it goes to this. So, this is the total energy in this elliptical orbit, and when it goes to the circular orbit, what is the energy now? So, you know that the radius is 4r. So, it will be minus k by 2a, you can use that and you get the change in the speed.